Welcome back to Statistics. I'm Dr. Jeff Groh. Today we're going to be talking about estimates, and sample sizes, and in particular confidence intervals. First, a point estimate is a single value that is used to estimate a population parameter. So, for example, x bar, the sample mean, is used to approximate the population mean, mu, just as the sample standard deviation is used to approximate the population standard deviation. These would be point estimates. On the other hand, a 1 minus alpha confidence interval it's an interval of values between, say, A and B, such that the probability of the population parameter falling in the interval is 1 minus alpha. We'll explain why we're doing this confusing 1 minus alpha thing here in a minute. So the probability that the parameter falls between A and B will be 1 minus alpha. I should mention that the population parameter doesn't have to be the mean. It could be any other parameter. So let's, in the spirit of calling parameters using Greek letters, let's just call it some parameter phi. In this case, 1 minus alpha is the confidence level, it being the probability, that's how confident you can be, sometimes called the degree of confidence, or even the confidence coefficient. I'd say confidence level is just fine. What is more, the boundaries or the endpoints of a confidence interval are called critical values . These correspond to critical z-scores. That we will study shortly. For confidence intervals, these critical z-scores have a notation we usually split the area in two for a standard normal curve. we'll put alpha over 2 area here and alpha over 2 area here, so the area in between is 1 minus alpha. You'll have 1 minus alpha probability, or confidence, that the value will lie within this interval. We split the difference on the alpha that's left over, half over here on the right tail, half on the left tail. This will be your critical z right here. This will be the negative of the critical z. There is a generic form for confidence intervals. We'll have the statistic minus e to the statistics plus e, where e is the margin of error, and it usually takes the form of a critical z-score times a standard error. An example of a standard error would be a standard deviation. So we've already seen things that could substitute for a standard error. The critical z-score will represent a certain number of standard errors that you can go in order to attain the necessary confidence. We'll choose the critical z to attain the confidence that we need. As an example, suppose that 36 samples from a soda dispenser show an average, that's your statistic, amount dispensed of 12.19 ounces. The standard deviation is 0.11 ounces. Find a 95% confidence interval for the mean number of ounces dispensed. Generally when you use this machine. So for our solution, we need to know that n is 36, greater than 30. So it's a good bet that the distribution of sample means will follow a nice normal distribution. We want a confidence, 1 minus alpha, of 0.95. 95% confidence, which means alpha, if you just look at this, would have to be 5%. 5% chance of error. We're going to suppose that the distribution of means will be normal. We're going to try to find where the mean of the sample means is, given our own mean, and we'll create some interval, a confidence interval. We'll be 95% sure that the mean of the sample means will be, which is also the population mean, will be in the interval that we specify. We don't know where the middle of this distribution is. We just know that it does exist, and we're willing to tolerate 5% error, which means 2.5% on this tail and 2.5% on the other tail. Alpha divided by 2 is 0.025. 2.5%. We'll split the difference on each side. So we find the critical z by putting alpha over 2 area on this side. That means over here we'll have 0.975. If this is 0.025, 2.5% in the right tail, from their left will be 97.5%. We can use this value to determine the critical z-score, the z-crit, which is our z alpha over 2. Alpha over 2 will be the area in the right tail, and everything else to the left. So we'll use the inverse normal function on the calculator. Remember that on the spreadsheet, it's not inverse normal or inverse norm, it's norm inverse. We also need to keep in mind that the sample standard deviation is 0.11, and the mean that we found, x bar, is 12.19. Step 1 in our solution will be to find the critical z. And we'll use the inverse normal to figure that out. So second distribution, number 3 on my calculator, is the inverse normal. The area will be 0.975. Remember, we want a 95% confidence. That means a 5% chance of error. The chance for error is split between the right tail and the left tail. So we'll have 2.5% chance of error in each tail. 2.5% chance of error in the right tail means the area to the left of it will be 97.5%, or 0.975. That's the area. We have to split the alpha in 2 and then subtract from 1 to figure out the area. So the area is going to be 0.0975. The mean is 0 and the standard deviation is 1. We're using z-scores, so we use the standard normal distribution. And so we get the z critical to be 1.9599, which I'll approximate as 1 point, with a 6 after that. I'll round this to 1.9600. So 1.9600 will be the critical z-score. On step 2, we'll calculate the margin of error. The margin of error will be your critical z-score times the standard error. In this particular case, the critical z-score is 1.96. The sample standard deviation was 0.11, but you might recall from our previous chapter that in the sampling distribution of the sample means, the standard deviation of the sample means is the standard deviation divided by the square root of the sample size. And so this will be the margin of error. From there, we can proceed to step 3 and calculate the confidence interval. So in step 3, we'll say that the left-hand endpoint will be the sample mean, 12.19, minus our standard error, 1.96, times 0.11 over the square root of 36, the mean, which is also the mean of the sample means. And that's less than 12.19 plus the margin of error, 1.96, 0.11 divided by the square root of 36. Let's crunch those numbers on the calculator and figure out what they are. Crunching these numbers, I have 12.19 minus 1.96 times 0.11 divided by the square root of 36 is 6. This gives us a left-hand endpoint of 12.154, going to one place more than in the data. And then on the other one, it's 12.19 plus 1.96 times 0.11 divided by 6. This gives us 12.226, rounding it in that last place. This is a 95% confidence interval. We don't know what the population mean is. We have a sample mean. The sample mean shouldn't be too far from the population mean. Whatever the population mean is, we may be 95% sure, based on this sample of 36 cups of soda drawn from this machine, that the population mean is between these two values. You should notice different samples will give different endpoints on confidence intervals having the same confidence level. I should make a note of that. Different samples will yield different intervals having the same confidence level. And that's okay. You don't always need to be 95% sure, but in all cases where we want to be 95% sure, the critical value will be 1.960. What if we want to be even more confident? 99% confidence. In that case, we'll only accept a 1% chance of error. We'll split that difference between the two endpoints, and the critical z ends up being 2.576. If you're willing to accept 10% error or 90% confidence, then the critical z will be 1.645. These are the critical z's that we typically will use in this course. So for means, provided the sample is big enough, we'll use x bar minus the z alpha over 2 times the standard deviation over the square root of n, which is the sample size. We'll use this only if the sample size is big. What are the confidence intervals for proportions? Remember that the population proportion may be p, the sample proportion will be p hat. We don't know what p is. We can figure out p hat from a sample that's large enough. So we'll have p hat minus our margin of error is less than p is less than p hat plus the margin for error. So how do you calculate the margin for error? That's going to be your z alpha over 2 times the appropriate standard error, standard deviation, your margin of error. You'll recall that in the binomial distribution, the standard deviation was the square root of npq. Here, the best we can do is the square root of n p hat q hat, where q hat is 1 minus p hat. But you have to divide it by n. And so you end up with a margin of error z alpha over 2 square root of p hat q hat over n, where the square root covers everything. That's how that simplifies. In other words, the confidence interval for proportions will be p hat minus z alpha over 2 square root of p hat q hat over n is less than p is less than p hat plus your critical z square root p hat q hat over n. For example, suppose that a polling company conducted a poll of 2,000 adults. That's the sample size, a very big sample size, and found that 382 regularly listened to AM radio. I guess for me it's guilty as charged. I'll listen to AM radio while I'm going to work or going home from work in the car. Find an 80% confidence interval for P, the proportion of adults who listen to AM radio. Also, find a 95% confidence interval. So there are two parts, part A and part B, 80% and 95%. Let me note that N is 2,000, and the number of respondents who said that they do listen to AM radio is 382. We're looking for on part A 80% confidence and on part B 95% confidence. We'll do this by hand, and then I'll show you how to make the confidence interval on your calculator in a very simple fashion. By hand the first time. Our sample proportion is 382 out of 2,000. The critical Z, we have to split that 20% error on each tail, so a 10% error on the right tail. What's the critical Z? We can find the critical Z using the inverse normal, where we're using 90% of the error to the left of that 10% right tail. We get 1.2816. Approximating our p hat, 382 divided by 2,000, we're getting 0.191. From this, it's easy to calculate Q hat. Q hat is 1 minus that. 0.809. Our margin of error then is going to be 1.2816 times the square root of 0.191, 0.809 divided by 2,000. Let's crunch those numbers. .191 times 0.809 divided by 2,000. I'm getting about 0.011. Now, to calculate our confidence interval, we'll take p hat minus e to p hat plus e, where this is our margin of error. So our 80% confidence interval will be 0.191 minus 0.011, 0.180, and 0.191 plus 0.011, 0.202. Okay, so this was a bit of work, but I'm going to show you a trick on how to get this from your calculator. Go to Stat. Just press the Stat button, and then go to Tests. Use the right arrow to go over to the Tests column. You need to go far enough until you get to the, on my calculator it says A, 1 proportion Z interval. We're going to make a confidence interval using z-scores for our critical z's. And it's using only one proportion. We only have one population and one proportion. There's a 2 proportion z-interval in the case that you have 2 different populations with 2 different proportions. But we'll talk about that later. For now, just type in 1 proportion z-interval, and it gives you the ability to enter the x value, 382, the n value, 2,000, and your confidence level, which is going to be 0.80. Hit calculate, and it will produce the same interval, rounded to this level. So we didn't really need to go through this crummy calculation. We could have just plugged the data into our calculator, and it does all of these calculations for us. It will produce the endpoints of the confidence interval. Let's do part B, where we're looking for a 95% confidence interval. We'll use our calculators for part B. We'll enter everything the same way as before, except now so stat, tests, 1 proportion z interval, 1 prop z int, 382, 2000, and the confidence level is 0.95. That's the difference this time. It gives us 0.174, rounding to 3 decimal places, and 0.208. Notice that this interval is slightly wider. than the previous interval, which kind of makes sense because here we're 95% sure. Before we were only 80% sure. If you have a smaller interval, you won't be as sure. The wider you make that interval, the more confident you can be that the population parameter will be in that interval. In interpreting this confidence interval, we don't know the true proportion of AM listeners based upon this survey, but we believe with 95% confidence that the proportion of those listeners is somewhere between 17 and 20%. Another thing to bear in mind is that we have a pretty good bound on the population proportion using only 2,000 individual responses. 2,000 is a very small proportion of the general population, and yet we get a pretty good confidence interval, 95% confidence that the population proportion lies somewhere in this interval. So you don't need huge sample sizes in proportion to the size of the population. In fact, the size of the population won't have much to do with the size of these confidence intervals. These intervals only depended upon the sample size. However, the sample did need to be representative of the population, and that means it needed to be a simple random sample. Convenience samples or other kinds of bogus samples, using internet polls or whatever, that's not going to hack it. It has to be a simple random sample in order to make these things work. What are the requirements to estimate population proportions in this way? Obviously, you need a simple random sample. Second, the conditions of a binomial experiment must be satisfied. And third, there must be at least 5 successes and at least 5 failures. In other words, NP hat is at least 5 and NQ hat is at least 5. Next, we'll show you how to determine how big a sample you need This is a little vague. Given a margin of error and a confidence level, how big of a sample size is required? And we're going to use this margin of error formula to solve for the number n right here. The way you solve for a variable is you whittle away at the things surrounding it, starting with the things that are furthest away by the order of operations agreement. And you use opposite operations. So this z alpha over 2, the critical z, is the furthest away from n, so you will divide it off. It's multiplied, so you divide both sides by that value. We'll have e divided by the z alpha over 2 is the square root of p hat q hat over n. The next thing you need to do is get rid of the square root. So you'll square both sides. E over z alpha over 2 squared is your p hat q hat over n. I want to solve for n, but n is in the denominator on the right-hand side of this equation. That's okay as long as we invert both sides. We'll have n divided by p hat q hat equals your critical z divided by your margin of error squared. Everything just gets turned upside down. Finally, we can solve for n. N will be p hat q hat times your critical z over margin of error e squared. You might object, how do we determine p hat and q hat until we have a sample? Well, here's the thing. If you have no idea what the proportion is, then use 1/2. If you have some idea of what the proportion is, maybe you can use those. Let me write that down. If an estimate for p hat is known, then use that. Otherwise, use p hat equals 1/2. That'll be 1/2, and q hat will also be 1/2 in that case. So in that instance, you'll have n equals 1/4 z alpha over 2 over e, quantity squared. You'll use this when you have no idea what the proportions are. One little caveat, and caveat is the Latin word for beware, a little warning. You always round n up. You never round the sample size down. Suppose I use this formula and I get n equals, say, 25.2. I'll use n equals 26. I won't round down to 25. You never go down, you always go up. As an example, suppose that you wish to determine the percentage of residents in your neighborhood who visit McDonald's on a typical day. If you have no preliminary estimate for P, how many people should you sample to obtain an 85% confidence interval with a margin of error of plus or minus 0.05, or in other words, to within 5%. Since it's an 85% confidence interval, alpha will be 0.15. 1 minus alpha will be 0.85. And the margin of error is 0.05. We're going to use p hat equals 1/2 and q hat equals 1/2. So we'll use the formula where we have no idea what the proportion is. The thing that's missing is the critical z. And for that, we need the alpha over 2. Which is 7.5%, 0.075. We'll use the inverse normal feature on our calculator. Second distribution, inverse normal. The area is going to be 92.5%. 1 minus alpha over 2 is 0.925. So 0.925, and the critical z is 1.440. I'll round it here. 1.440 will be our critical z. It follows then that the sample size should be 1/4 our critical z, 1.440, divided by the margin of error, 0.05, squared. Crunching the numbers on my calculator, I'll have 0.25 times 1.440 divided by 0.05 and then squared. I'm getting 207.36. Your sample can't be 207.36 people, and you must round up. So your sample size will have to be 208.